Okay, first off, differentiation. If you've got y is x to the power of n, then dy over dx is nx to the n minus 1. Basically all it's saying is, say you've got y equals x cubed, you are going to take this power in front of the x and then take the power down by 1. Okay, so the power just goes from up here to in front and the power drops by 1. Okay, so power goes in front, drop it by 1. And you can just do that for each part of the equation. So work your way through. If you had 2x to the 4, you would then go, right, so the 4 is going to go in front, so 4 times 2 will give me 8, and then the power goes down by 1, x to the 3. Okay, nice and easy. You might notice that dy over dx is short for the difference in y over the difference in x, which you might remember from gradient. So when we're working out dy over dx, we're actually working out the gradient at a certain point without having to actually calculate the difference in y and the difference in x. This does it for you because it actually gives you an equation in which to do it. So dy over dx is for when you're trying to find the gradient, which is why we use it when we're trying to find the gradient of the tangent, things like that, which you can then use to find the gradient of the normal, which is all stuff that you should hopefully remember from Core 1. So for integration, if you've got this sign, the integral of x to the n dx, it's basically taking you back the other way. So it's saying, what did we differentiate to get this? So the power goes up by 1 this time, and you are dividing by the new power. So power goes up by 1 and you're dividing by the new power. You could have written it as x to the n plus 1 over n plus 1. It depends on personal preference. I prefer to put it as a fraction before. Same difference. This plus c is important because if you differentiate a number, like 6 for example, it disappears because there's no power of x. So we could have differentiated any number, any constant could have been added on here, and it would have disappeared when we differentiated. So when we integrate to get back up to what we started with, we need to add on a plus c, which we can then work out if we know a coordinate that works with it and so on. If they give you something to integrate between, so say you had a value here and a value here, then you wouldn't need to put in this plus c because you don't need to worry about it anymore. To give you an example of how our integrating works, if you've got the integral of, let's go with x cubed, then it turns into, let's do it properly, x cubed dx, then it turns into, power goes up by 1, so we get x to the 4, and we're dividing by the new power. So I'm going to write it as a quarter, x to the 4, okay, plus c. So if you've got a more complicated one, let's go with 3x squared dx. Then power goes up by 1, so we get x cubed, and we're dividing by the new power. So we're taking our original number here, and we're dividing by the new power. So 3 divided by 3, actually just going to give me 1. So I get x cubed and plus c. So you've got to bear in mind what effect dividing by this new power will have on what your original number was. That's why I find it's easiest to write it as a fraction beforehand, because it's easier to see that, for me, if we then divide that by 3 or multiply it by a third, it will cancel it out. Entirely up to you, it is personal preference. So that's our integration side of things, and integrating is used to find the area under a curve. So we can integrate to find the area under a curve, and you could have two values, get a value here and a value here, and that would tell me that if I'm looking at a curve, I can work out the area underneath it. So let's say we're trying to integrate this to find the area between 1 and 4 under the curve, so the bit that's coloured in yellow. We would start by writing it as, we'd be finding the integral of x cubed plus 1 dx between 1 and 4. So we would then integrate this bit in here and see what we get. And we would get, so the power goes up by 1, we're then dividing by the new power, and then for this bit, it's just a number. So at the moment, let's presume we're working with x to the power of 0, which is 1. So we're going to put it up to x to the power of 1, which is just x, and we're dividing by the new power, so the new power is 1, we don't need to worry about that. And because we've got values here, we don't need to put the plus c part. So we're going to do this, go between 4 and 1. And what we would do is we would work that out for 4, so we'd do a quarter, 4 to the power of 4, plus 4, here. And then we would, so for now we'll call it f of 4 for argument's sake. And then we'd be taking away f of 1. So f of 4 is basically working out all this area here, right the way back to the y-axis, that total area. So by working out f of 4, we're working out the total area up to there. We're taking away f of 1, which is this little bit that we didn't actually want. So we can use integration to find the area under a curve. If, however, it tells you you can't use integration and you have to use a different method, then that different method is the trapezium rule, and it looks a bit like this. So let's say we're trying to find the area under the curve for this function, y equals x squared minus 2x plus 3. So what we're going to do, we're going to find between 0 and, let's go with a bit about 2, we want to find the area under the curve. And we can do that by splitting up this area into a series of trapeziums. It will usually tell you in the question how many trapezium you need to use, trapezia I suppose they are, and it'll say how many strips it wants. How many ordinates will be how many different bits you're using under here. So there'll usually be one more than the number of strips that you've got, but they'll also tell you how many strips. So in this case we're going to do it with 2 strips. It won't be very accurate because the more strips you've got, the more accurate it will become. So if you look, we've turned that into 2 trapeziums. So at the moment it's going to be a bit of an overestimate because we're actually going to get this bit, and we don't want those. But for now this will do. So we've got that, and we've got this, and that's going to be 1. So we're going to work out the area of these trapeziums. So what we're going to do first of all is we're going to remember how we find the area of a trapezium, which you might be scratching your head over, so I will write it down for you, because I'm feeling nice this evening. We'll have half times the height, and the height in this case is this part, okay, and we're timesing it by a plus b. So basically what we're saying is, if you've got a trapezium, hold on, let's do this down here. Okay, that's not wanting to work, so we'll try this a different way. If you've got a trapezium that looks like this, and you've got a matching trapezium but upside down, that then looks like this, you effectively have made a parallelogram. And the way you find the area of parallelogram is you do the width times by height, perpendicular height. So in this case, if this was our A and this was our B, our parallel sides, that will be an A and that will be a B. So altogether, our height is still h, but our width is now A plus B. So this part of the formula, the h and the A plus B, comes from this idea. The half part is because we put 2 trapeziums together, we only want one of them. So let's just get rid of this. Right, so we've got half the height times A plus B. So in this case, the A and the B are going to be this height and this height, because they're the parallel sides. So your first one is going to be f of 0, so you're going to put 0 into this equation. So our first trapezium is going to be half times, now the height in this case we can see is the width of the strip, which is 1. You've got to make sure that you put in the correct height, otherwise it will mess everything up. So it will tell you the width of the strips, or you should be able to work them out. If it asked you for 4 strips, we'd be putting in 0.5 here, because we'd be doing this distance of 2 divided by 4, but for now we're just going to stick with 1. So half times 1 times by, and then we've got a plus b. So our a value is going to be f of 0, and our b value is going to be f of 1. And that's our first trapezium. The second trapezium is going to be the exact same thing, only we're going to have f of 1 and f of 2. Now, what you might be able to see is the more strips you get, the outside edges only get counted on the outside trapezia, whereas the inner edges get counted as part of this trapezium and as part of this trapezium. So there is a shortcut rule that you can use, which is explained reasonably well in the formula book, which is that you would do half times the height times by the outer coordinates added together, and then you use 2 lots of each of the inner coordinates. It's just basically a way of adding all of this together. But if you're not very confident with the idea of doing this, the best way to do it is just to create your trapezia and work out the area of each one separately and add them together, rather than just plugging things blindly into a formula, because it won't be obvious where you've gone wrong if you do go wrong and you're just sticking stuff in a formula. So for this one, we would work out what f of 0 is, and we would go 0 squared minus 2 lots of 0 plus 3, so this would be 3 here. So if I pop that in there, in fact I'm going to use a different colour so I don't get confused. That's going to be worth 3, and then f of 1, we're just going to go 1 squared is 1, take away 2 lots of 1, so then minus 1 add 3 gives you 2, and then we know that that one's going to be 2, and then for f of 2 we're going to do 2 squared, which is 4, take away 2 lots of 2, which is back to 0, and then add 3, which gives you 3 here. So it makes sense, we're being fairly symmetrical about our graph, and we would then work out what these add up to and then add them together. Okay, so that would be our total area of the trapezia, which is giving us an estimate for the area under the graph between 0 and 2. So it's just working out the area of a trapezium, so you need to be able to remember the formula because they don't give you it anymore like they used to at GCSE, and you've got to remember that the height is the width of the strip and the A and the B are the values, the y coordinate at those points for x. So it's basically f of that number, where f is the function that you're doing to y, to get y in terms of x. So trapezium rule, not as complicated as it looks, I promise. It's just a case of remembering how to find the area of a trapezium and applying it to your picture. If in doubt, draw a diagram. It does really, really help.